to apply them to some very simple processes of interactions between electrons and positrons. And the main goal will be just to reproduce the formulas of classical electrodynamics. So we will see how one can compute the potential of interaction between, say, two electrons. So what we'll study is the scattering of an electron on an electron. And using Feynman rules, we can calculate the amplitude of this process. So let us see. So we have, say, this electron has momentum P. This has momentum so suppose that this has momentums P and spin S, and this has momentum K and spin R. And so in the final state, the electrons have momentum P prime, spin P prime, and momentum K prime, spin R prime. So we need to draw the diagrams that describe this process. So we have two electrons in the initial state and two electrons in the final state. So the simplest diagram that we can draw is this one. Another possibility is that we connect the lines in a different way in the final state. And you can see that there are no other diagrams that can contribute. So we just need to compute these two diagrams. And the second diagram is basically obtained from the first by interchanging the electrons in the final state. So it will be the same up to interchange of PS prime with K prime R. So we can immediately write down the amplitude, starting with the first diagram. So how do we calculate the amplitude? We just need to multiply all elements that appear in this diagram. And so what elements do we have? We have initial and final wave functions. So initial and final states correspond to the wave functions of the electron. And so in the final state, the functions will be S prime, P prime, and this will be U bar R prime of K prime. So the the best way is to go, okay, along the electron line from right to left and multiply all elements that we have. So in the vertex, is given by minus IE gamma mu. So this vertex will be minus IE gamma nu. So if we multiply reading along this line from right to left, what we will get is, well, minus EI will appear twice. Then we will have U bar S prime of P prime, gamma mu US of P, and then U bar R prime of K prime, gamma nu UR of K. And finally, there is a propagator for the photon, so which will depend on the momentum. And what is the momentum flowing along this slide? Well, by momentum conservation, this is equal to P prime minus P, which is the same as K minus K prime. So the photon propagator is equal to minus I G mu nu divided by P prime minus P squared. So this was the contribution of the upper diagram. Now to add the lower diagram, we need just to interchange the two outgoing lines. And since these lines describe particles that obey the Fermi statistics, we need to change the sign. So this is obtained just by interchanging the particles in the final state. So this is the full answer, yes.
Since now we're dealing with gamma mu, which is a matrix, it would seem as though the order of multiplication is important.
That's right.
And so you said read the diagram from right to left, which implies an order. Any particular reason why that order? Or
so we read along the so any fermion line either forms a closed loop or it goes from well, initial to final state. And so we should read from the end to the beginning of the line, because this will be a matrix element of yeah, so it will have the form U bar times some gamma matrices and then U always. So so that was the reason. Okay, so yes. This particular case, because this here the line ends here, so that we need to read electron lines against the flow of charge, so in the opposite direction to the arrows.
So what about these two lines are parallel to each other? So you first read the first line on right to then you read the second line on right.
Yes.
And also, so this diagram is the improvement between
Here they are indistinguishable because they're both electrons. So that's why we have two identical answers. So anyway, this is just the answer, and well, the question now is what we can do with it. And one thing that we can, so it doesn't look, I guess, as anything you have seen before, unless you had quantum field theory course before that. But the physical setup here is, of course, very familiar. It's just electrons interacting with electrons. So, for instance, if we consider the case where these electrons are just static, so that they, well, they sit in some point in space and don't move at all, this would be described by, well, not even quantum mechanics, just by classical potential theory. So what I will do with this formula is just I will I'll show you how to recover this simple classical picture from quantum field theory. So we will study the non-relativistic approximation to this formula. So in the non-relativistic approximation, we assume that the momenta of incoming and outgoing particles are much smaller than their masses, so their velocities are smaller than the speed of light. And then we know that for spinors, in the non-relativistic approximation, we obtain the following formula. Well, actually, this was obtained for the static spinor. So what we'll do, we'll just use this formula without any corrections. One can, of course, one can add corrections that depend on the velocities of spinors, but this will be of higher order. So we can compute now this spinor products by substituting the formulas here. So, well, what do we need to calculate? We need to calculate U bar S prime gamma mu, and so let's compute first the case where the index is equal to 0, US. So you see now the dependence on momenta drops out in this approximation. So this will be equal to just U S prime dagger US. And this is what? So this is because U bar is defined with multiplication of gamma 0 from the right. So gamma 0 cancels. And so this is equal to, well, I'm sorry, here there's no 2. So this will be equal to 2m gamma s dagger, gamma s prime dagger gamma s. So psi prime psi s. And so this would be equal just to 2m delta s prime s. So the formula that we obtained the other day when we studied the various solutions of the Dirac equation. So now let's calculate the same matrix element for the spatial components of the current. So what stands here is nothing but the current. It's just the space-time current of electron being scattered on another electron. And what we are doing here is we are computing this current for electron, for the static electron or non-relativistic electron that doesn't change its velocity much in the scattering process and is initially moving very slowly. So then we need to compute this, and here I have to remind you how the gamma matrices look like. So the gamma 0 is off-diagonal unit matrix, and gamma i's are just built from the Pauli matrices. I think the sign convention was like that, or maybe it was opposite. Yeah, it was like that. So, and then we need to multiply by xi s. Okay, so now my claim is that this is 0. Can you see this immediately? Well, if you multiply the matrices in the middle, what you get is the diagonal matrix with the gammas, with the sigmas on the diagonal, and we take it sandwiched between the analogous, between the same two spinors. So it will be a difference of two terms which are of the same form. So this is 0. So again, this is what we expect. So if you have electron that has 0 velocity, so what is its current? Its current is just its, well, it will have 0 electric current and will have certain charge density. So this is the charge density of a static electron, well, this is the current which is 0 for when electron doesn't move. So the physical meaning of this formula is very simple. But then what does it mean? This means that we only keep, so summation over new indices is, well, we only keep the index 0. And so this formula simplifies a lot. So the only remaining thing that we need to calculate is what is p prime minus p squared. So this will be the energy of p prime minus energy of p squared minus the momenta, the difference of momenta squared. And so this can be written as, well, so this is equal to square root of m squared plus p prime squared minus m squared plus p squared. So you see, in the non-relativistic approximation, this is very much close to 0 because the leading order, so the momenta are much smaller than the mass. So this will be equal to the difference between kinetic energies, p squared prime over 2m. We expand the square roots to the power series in p squared. So this is approximately the difference between the kinetic energies, which is, so if we compare this term to that term, so this will be much smaller because it is suppressed by the ratio of p squared to m squared. So this is quartic in momentum, and this is quadratic. So we can just approximate this by p prime minus p spatial squared. So all in all, if we substitute this to the formula for the amplitude, so we see that okay, so there was we should be really careful with signs. So there is minus I squared that gives a minus. This cancels the minus in the photon propagator. G00 is plus 1. But there is another minus that comes from here. So in total, the amplitude will be negative. Then what we'll get is a factor of, let's say, 2m squared. This comes from normalization of the external wave functions. And this is the only remnant left from the matrix elements of the spinors. And so here we'll have E squared divided by P prime minus P squared. And finally, we will have, well, some delta functions. So delta S prime S, delta R prime R, minus delta S prime R, delta R prime S. So this is the final answer. This is, well, approximate. We've thrown away some terms that are suppressed in the non-relativistic limit. So now we have to compare it to, well, to what we would get in, say, usual quantum mechanics. So in the usual quantum mechanics, when we have two particles colliding, the scattering amplitude is just a Fourier transform of their interaction potential. This is the Born formula. So let's compare it to the Born approximation. So in the Born approximation, the Born amplitude is equal to minus, and then the Fourier transform of the interaction potential. Now, in comparing to the Born formula, it is important to remember that the amplitude actually depends on how we normalize the wave functions of the incoming particles. So in principle, the amplitude, well, it's defined as a matrix element of evolution operator between initial and final states. And so it does depend on normalization. In principle, we should, if our wave functions are normalized to something different from 1, we should divide out by these factors. And this, in fact, it means that we should not consider this prefactor. So we should drop this 2m squared from the formula when we compare it to the Born amplitude. So this is just normalization factor that arises because the wave functions in quantum field theory are normalized to the twice the energy of the particle instead of being normalized to 1. The reason being the relativistic invariance. Yes.
If we've been using our m to calculate, or if we would use the m's that we've been calculating to calculate probability, then shouldn't this exclusion of the normalization factor be part of the algorithm for calculating?
Exactly. Yes. So one has to divide by this factor. That's that we'll learn. I'll show you what precisely what factors you should keep, and there is a formula how to go from m to the probabilities. Anyway, so far we want just to compare to the Born amplitude, and then we see that okay, so that the potential is so we know the Fourier transform of the potential, which is this formula. And so to compute the potential in as a function of x, we need to invert the Fourier transform. So this will be equal to the Fourier transform of 1 over q squared. Okay. And so the Fourier transform gives e squared divided by 4 pi r. So this is the Coulomb potential. So we derived it from quantum field theory. So the yes.
For our non-relativistic approximation of m, for the very last step, for the exchange of p prime and k prime, are we assuming that p prime minus p squared is approximately k prime minus p squared?
No, not really. But so we have two identical particles, right? So so by Fermi statistics, the amplitude should be, if you interchange the particles in the final state, we should interchange. We should change the sign. So the best way to arrive at this formula is to assume that to put labels on the final state particles so that they're really different. So we can say that, for instance, we scatter electron with spin up on electron with spin down. Okay, so and then we can distinguish which one is which, and then only this term contributes. So then we can, for instance, take S equals spin up and R to be spin down, and then S prime is spin up and R prime is spin down. And so in the non-relativistic approximation, interactions cannot flip spin, so which we can immediately see here. So then only this term will contribute. And then we get our potential. Okay, so the conclusion here is that the Coulomb interaction between electrons that we understand very well, and of course this is by far not the easiest way to derive it. In fact, arises as a result of exchanging of a photon. So the force of electromagnetic repulsion between electrons is a result of photon or a virtual particle running between, well, in the Feynman diagram language, it will be exchanged between the electrons and positrons. So you see that in quantum field theory, the forces are described in the same way as particles. So the quantum field of photons, on the one hand, it describes radiation. So if there were photons in their final and initial state, we would describe them by the quantized electromagnetic field. But on the other hand, they also describe the force between electrons and positrons. Yes?
Why should the probability amplitude be the sort of thing that a potential is?
Oh, we just, okay, so. So this is a way to define what we mean by potential. So here we are computing, we can compute the outcome of scattering of two particles, right? So if you wish, that defines, how can we, this is what would be one way to measure of the strength of their interactions. And so mathematically, we just define the probability, the potential as the Fourier transform of the probability. Now, suppose that we want to study electron-positron scattering. So, by the way, this you can improve this formula by not making any approximations. So one can just compute with the amplitude for arbitrary momenta, and then this formula. So the exact formula was obtained by, I think, by Müller. So this process of electron-electron scattering of relativistic electrons is called Müller process. So actually this process is called Müller process. And electron-electron scattering was studied by Baba. Actually, well back before the quantum field theory was introduced. Anyway, so if you study this process, then what do we get? So the diagrams that contribute now are, well, at first it might seem that we just don't need to do anything new, right? Because this will be the same diagrams. But it turns out that there is a subtle difference related to the fact that the arrows on the lower line will now be different, okay? Therefore, the second diagram, instead of crossing the initial and final lines, we will draw the diagram that corresponds to annihilation of electron-positron pair, which then produces an intermediate photon, and this photon recreates electron and positron in the final state. So there are these two diagrams to compute. So suppose that this has momentum p and spin s. This has momentum p prime, spin s prime. Same for the positron. Then what will be the amplitude? let's write down the answer for this diagram and for this diagram separately, because now they are different. So in this diagram, what do we have? So we should write an overall minus IE squared. And then we will have the matrix element U bar S prime of P prime gamma mu US of P. So this corresponds to reading the upper line. In the lower line, on the contrary, we should read from left to right, from the initial state to final state. So this corresponds to V bar. So the initial state positron is described by the psi bar field. So it appears with the barred spinor wave function R of k gamma nu V R prime of k prime. Then we should write down minus I g mu of p minus p prime squared. And there will be an extra minus sign. So this extra minus sign comes from, well, disentangling from the weak contractions. So if you do it even more carefully by first writing down the amplitude as a matrix element and do the weak contractions. So in this weak contraction, in this matrix element, you will need to interchange the psi's. And so in this calculation, this interchange, so you need to do an even number of interchanges, and here you have to do an odd number of, yes?
Aren't we supposed to be able to read off the expression for M just from the diagram without doing the contractions? So where would we see the minus sign just in the diagram?
So, okay. I don't know. The answer, well, the practical answer is that if you need to do any calculation, you first, so the diagram is just a crutch. It's better to write down the matrix element. And okay, so the diagrams tell you what structure weak contractions will have. And so then you carefully do all the weak contractions, and that way you never make a mistake. So you get all the symmetry factors right and all the signs right. So the diagram is just a nice graphical way to represent the answer. Yes? Yes, sure. So the index. Well, one has to do all the calculation. I would like to avoid this. It's written in the notes, but it's a little bit, I mean, it will take too much time. So just, if you want to see the details, just write down the elements yourself and see how weak contractions go, and then you'll see that there is a minus sign. So the second diagram, so in the second diagram, So what do we have? Well, we have now we read this line, and it starts with the V bar. U S of P, and then U bar S prime of P prime, gamma nu, U of V R prime of K prime. And then minus I gamma mu nu. But the momentum flowing through the photon line will be different. So here the momentum is what? It's P plus K. So this will be equal to, the denominator will be different. And so here we don't need to do much work because it's very similar to what we have in the electron-electron case, up to a minus sign. So the only new ingredient is the second line, but it's very easy to see that in the non-relativistic approximation we can just drop it, because the denominator in that diagram is very big. So P plus K squared. Well, what is it? It's E of P plus E of K squared minus P plus K squared. And here there's no minus sign between the energies. So to the first approximation, this will be equal to 4m squared. Yes?
Get an expression for IM, we add together the expressions that are associated with the diagrams. So why do we have an IM associated with diagram 1 and an IM associated with diagram 2?
Oh, so this is for 1, and this is for 2, and we should add together. We should add them together. But so the point I'm trying to make is the second diagram is very much suppressed in the non-relativistic limit. Yes. Maybe I expressed myself not completely clear. But we read each line from the end to the start. So we start from the end of each line. So this would be V bar, and then gamma, and then U. So here we start with the U bar, and then another gamma, and then V. So that way we get.
You can choose this. It doesn't matter if you write this line first and this line second.
Yes, it doesn't matter, of course, because this is just
as long as you
this. Yeah.
when you are writing one line, you should start from it.
Yes. So because this is all gamma matrix indices are contracted here and here, so this is just numbers. So anyway, you see that this diagram has huge denominator. So it's the rest mass of electrons squared compared to the denominator here, which is the difference between their velocity squared. So we can consider arbitrary slow electrons, and so in that case there will be a very, very small denominator here. So in a sense, well, what happens is that this photon is almost on shell. Okay, so it's so what flows here is the difference between momenta of the initial and final electrons. Okay, so this is the difference between their momenta and form momenta, and the most important part is the spatial momentum. And that's very small. Now the momentum flowing through this line is the center of mass energy of the electrons. So the form momentum here has a very big time-like component. So the energy, so here what we get is the flow of energy, and here we have the flow of momentum. And in the non-relativistic limit, momentum is much smaller than energy. So this diagram is very much enhanced compared to that. So we conclude that M1 is much bigger than M2. And so in the non-relativistic approximation, we can only keep the first diagram, which then gives the same matrix element as here, up to a sign. So this will be equal to 2m squared, E squared, P prime minus P squared, and then delta S S prime, delta R R prime. So if we compare with the Born formula, we conclude that for E plus and minus, the potential differs from the case where we have electrons by sign. So we will get the negative potential, the negative Coulomb potential. So this is the, well, reproduce the well-known conclusion that the like charges repel and the opposite charges attract. Let's make a break for a couple of minutes, okay?